Okay, now we're ready for the third topic for this week in our video lecture, which is tree data structures. Now, I want to make it clear that as we're talking about these are just sort of introductory. You're going to see trees and linked lists and stacks and queues and other kinds of data structures in future classes. In 2100 and 2110, you're going to spend a lot of time on these, especially implementing them. You'll probably see them again in more advanced detail in 3110 and 4110 if you're a computer science major. So I'm just introducing you to them. I'm mostly introducing you to them theoretically. We're not worried as much about code implementations of these. You can certainly find them on the internet as well. And these are things that are tried and true and been around for a long time. So it's not necessarily a problem if you use code that you find on the internet, except in assignments where it specifically says you're supposed to do your own work in class. But certainly in the real world, and a lot of these even have implementations in the standard C library. Like there's a B-trees binary tree implementation in the standard C library. And there's also ones in C++ standard template library that we'll be discussing at a later date. So I want you to understand the concept, understand how they might be applied to certain kinds of problems, what problems they're used to, and then you'll get more experience manipulating them and working with them in some future classes. So let's take a look at trees for a little bit. So the idea behind a tree is a tree consists of nodes, and again the nodes could be data along with some pointers, just like a linked list, but a little bit different way to organize them. And in general, each node in a tree can have 0 or more children. Notice the or more. So in this first example, this is a generic tree. This root node or parent node, the ultimate parent, if you will, has 3 children. This particular parent has 3 children. This one has 1, and this one has none. You can only have one parent, so this is we can't really draw the complete analogy to at least the traditional nuclear family, if you will, because you only have one parent. But the parent-child relationship is still a convenient way of thinking about it. Then we have some specialty kinds of trees, and one of the ones you're going to hear about a lot is a binary tree. And binary trees have 0 to 2 children, so you can't have more than 2. So in this case, this parent has 2 children, this parent has 2 children, this parent has 2 children. So we call this a balanced tree. Every parent has 2 children. So we could have parents with only 1 child or with no children. In fact, actually, if we look at these nodes down here, they don't have any children. They're also the end of the tree. We call those leaf nodes, as you'll see here in a minute. So a binary tree is balanced that way. Use of binary 1, 0, meaning only 2 values. So these are useful for representing certain kinds of data and in certain kinds of situations, and we'll see some examples of that here in a minute. So the root is the one with no parents. It's the one at the top, although when you think about tree roots, you think about them being at the bottom. A leaf, these down here are the ones with no children. An interior one is also called a non-leaf. And then the height of the tree is the distance from root to leaf. And in this case, it's pretty easy because we have all the levels as being kind of symmetrical, even though some of these parents have 3 children. This is not a binary tree. We could have, for example, if this guy over here had 1 more child, then the height of the tree would be 4 instead of 3, even though all the rest of them don't. All the rest of these down here don't have children. So it's the height of the longest span of the tree, if you will, is considered the height of the tree. So the height, we could say this is distance from root to farthest leaf, if you will. What we'll really look at here is layers, if you want to think about it that way as well. So a binary tree or a binary search tree, we use binary trees a lot for searching. The idea is that at each node there's a value, and as we put the values into the tree, they're not in a specific order in terms of the way you would think of like alphabetical, but the idea is that at any node, when I insert something into the tree, if it's a smaller value, I put it to the left. If it's a larger value, I put it to the right. So y, it comes before x, so it would go to the left. Z would come before y. Now if I added, for example, an a, it would go, a is smaller than x, so it would go to the left, and it's also smaller than y, so it would go to the left. If I added, something, it's kind of hard since I'm at the end of the alphabet here. If I added something that was smaller than x but larger than y, then it would go to the right of y. Okay, so you get kind of the general idea. So it allows me to fairly quickly find something because I've kind of split the problem in half. Because everything that's smaller than this one is this way. So if I know what's smaller than this one, I know if it's there, it's going to be over here on the left side somewhere. I just have to keep going until I either find it or until I hit a leaf. So notice this is a lot like the binary search that we talked about in 1030, where if we know things are ordered, we can essentially go to the middle and eliminate one half or the other of the data very quickly. That's essentially what this tree implements. If you think of a line going down right through the middle, we've kind of split the problem in half based on this value. Now, in this case, if it's x and we're talking about the whole alphabet, we really haven't split the problem totally in half because there's not that many values that are smaller than x in this case. So one side of the tree is going to be much bigger than the other if we had the whole alphabet, but that's okay. So here's some examples of, on the left are binary search trees. So to the left we have 10, so we have 10, to the left would be a 5, and then 2, which is not only less than 10, but also less than 5, also to the left. Here we have a bigger one, 30. 25, which was bigger than 10, but it's less than 30, so it goes to the left. And then 45, which goes over here. And this one's a binary tree, too. It's certainly not balanced, although this one didn't either. Each one doesn't have 2. This one is not a binary search tree. So I'll let you look at that one for a minute and see if you can find out why it's not a binary search tree. Hopefully you found it. The problem is this 25. This 25, well, yes, it's bigger than 5, so it's to the right. It's also bigger than 10, so it should have been over on this side. So it does not fit the definition of a binary search tree. It is a tree, but it's not a binary search tree because we would never find the 25 if we followed the normal rules, because we would have gone down this side and we wouldn't see it. Well, this is an implementation of a binary tree using C++. So I'm going to skip over it, but we'll look at it later. But let's take a look at these examples of finding something. So if I wanted to find something in a binary search tree, I would tell it where to start, which would normally be the root, and then the value I'm looking for. And so if I were looking in this tree, 2 is less than 10, so I go to the left, and 2 is less than 5, so I go to the left, and there I found it. Okay. In this tree, all these values were bigger than 5, so they were on the left. The only value smaller was the 2, and so I find it in just one step. So you can see the number of steps. So the number of steps will never be longer than the height of the tree, but it certainly might be less. So the height of this tree would be 3. The height of this tree would be 5, because it's 5 values from the beginning to the end on the longest side. Okay, here's a couple other examples. So if I'm looking for 25, that would be greater. So I go this route to the right the first time, but it's less than 30, and there I found it. And over here, I go left. I'm sorry, right, because it's greater. But then I would go left, and then I'm looking for 25, which is still left, but then to the right after 10. So here's some other terminology. A degenerate tree is a binary tree where there's only one child. So this would be an example of a degenerate node. Each node has only one child. A complete is one that has, everybody has 2 children, so that'd be this one. And a balanced tree is where most have 2 children. And there's more formal definitions that you'll learn about later, but these are sort of intuitive ideas. So this one's balanced. There's mostly 2, same number of levels pretty much. This one's complete, and this one's degenerate. Properties. For a degenerate tree, the height is order n if there's n nodes. It's basically a linked list if you think about it. In a balanced tree, the height is order log n. So the log of n, log base 2 if you will, because we're talking 2 children. So this is a really useful type for doing searches. Some other things that we can know about the tree is the time that it takes to do a search is proportional to the height of the tree, which makes sense, because in worst case I'm going to have to go all the way to the leaf, but I may not always have to. For a balanced binary tree, it's order log n, because that's the height is basically log n. For a degenerate tree, it's order n, because remember, degenerate tree, pretty much the height was the same as the number of elements. So then it's like searching an unsorted array or a linked list. How do we build and maintain them? How do we do insertions, deletions, and maintain various properties? Of course, maintaining the properties is easy as long as we make sure that we always put smaller values in the left subtree and larger values in the right subtree. Insertions and deletions, we're always going to insert sort of at the leaf level, but we're still going to maintain these rules. Sorry. I'm also cooperating all of a sudden. Let's go back up to where we were. Okay, so let's look at an insertion. So the algorithm for an insertion is that, first of all, we have to search for a value x. And if we don't find it, we're going to end at some node y, if x isn't in the tree, based on going right or left at each position. If x is less than y, then we'll insert a new leaf, if you will, at on the left of y. And if x is greater than y, then we'll insert one on the right. And in general, this is going to be order log n for a balanced tree, although the insertion may, in and of itself, unbalance the tree. So here's an example. If we're going to insert a 20, for 10 we go to the right because it's bigger. For 30 we go to the left because it's smaller. And for 25 we go to the left, but there's nothing there, so that's where we would insert it. So it would be on the left side of 25. For a deletion, and notice these algorithms you could implement in any language, including C or C++. First we have to find x. If it's a leaf, we can just delete it. Otherwise, if it's an internal node, we have to replace it with the largest value on the left subtree or the smallest value on the right subtree, and then move everything else up, basically. So let's look at an example. So we're going to delete 25. In the case of 25, it's easy because once we find it, it's a leaf, so we can just delete it. If it's an internal node, like we're going to delete 10, a 10 happens to be the root, so that is sort of a major deal. So we have to replace 10 with the largest value in the left subtree. And why the left subtree? Because they're the smaller values. So we couldn't replace it with a larger value because then that might screw up the fact that it's what's going on the left-hand side. So we replace it with a 5 and then move the 2 up, so the 2 goes away. So now we have an unbalanced tree, but all the rules are still in place and functional. Here's another example of deleting 10 with the smallest value in the right subtree, so we could also do it that way and move the 25 up. Now why the smallest value? We can't place it with the one right below it because that might or might not still be larger than some of the ones on the left-hand side. So we can move the smallest value up and do it that way, which we're guaranteed that it'll still be larger than all the ones on the left-hand side. So we can have different kinds of balanced search trees. We can have ones that are height balanced versus weight balanced, and we can move things around, sort of what's called tree rotation, in order to balance that after we do an insertion or deletion. There's other kinds of really common non-binary search trees that are used, and you can find algorithms for these. There's a 2-3 tree, where each internal node has 2 or 3 children, so it's not true binary because it's not just 2. Sometimes they can have 3. And all leaves are at the same depth, so everything's balanced so that there's not one side of the tree that's longer than the other, so the height on both sides is the same. Also a B tree, which these are ones where there's library functions for those. It's sort of a more general version of the 2-3 tree. So each internal node can have between k over 2 and k children, where k is the height, if you will. Each node has an array of pointers to children. This is used a lot in databases to create search indexes and stuff. There's also parsing trees. This is when we want to convert textual representation to a tree representation. We do this in a number of different places. It's done in XML to understand what the structure is, but you can even use this to create sort of sentence diagrams, if you remember doing those in like high school and stuff, diagramming sentences. That's essentially what a parse tree is. We can separate out the verbs and the nouns and the adverbs and the adjectives and all that kind of good stuff, and the articles and stuff, and create a sentence diagram as well. So like here's an example of a parse tree for an arithmetic expression. So we're breaking up the expression so that we can evaluate it. So notice in this case, the root is the operation in the middle that joins the two larger clauses together, and that's a plus. And then the next level is the operations on either of the two clauses. So in the case of the left-hand side, it's a minus, and then there's an a for one of the arguments, and then there's a whole other expression for the other one, which is a multiply, and then it has a 2 as one of the arguments, but the other argument is complicated again. It has a divide and then a c and a 5. So you can see how that bigs up that side. The other side, the percent, we have a 4, so that's a leaf. But then on the other side, we have another operation, a multiply, so we have to go one more level, and that's a d and a 5. So now we can evaluate this expression sort of bottom up, do the work, and get the correct answer, preserving all the parentheses. And this, by the way, is how some of the RPN calculators, you ever had one of the, maybe your parents have one of the old HP reverse Polish, what we call RPN or reverse Polish notation calculators. That's how they worked. So then we have different methods for traversing the tree. There's an in-order traversal where we eventually visit every node in the tree. So we do the left side and the right side, and that would help us to evaluate this kind of thing. There's also preorder and postorder, in which case we would visit them in a slightly different order, and we get output that shows like the output there. So we still end up being able to evaluate the expression, but it looks kind of weird, but that's how the reverse Polish stuff worked. Also works with XML. So if we look at this XML, which kind of looks like HTML structure, so we've got a tag called dependency, which has a closing tag at the bottom, and then objects, and then it depends on various things, and we could create the different clauses. So if you notice, each child of the dependency tag is basically one of the subtags inside there, and then what it is modified by, or what its object is, like a particular file. So you can see that structure very easily then there, and that would allow us to process it. Later on, you're also going to do a lot with graphs. I guarantee you in 3110 and 4110, and even in 2110, you're going to be working with graphs. These are used a lot. Graph theory is a very active area of research, and it's used in all kinds of industry applications. This particular example might be an airline network, for example, where the nodes indicate places an airline flies to, and the line segments represent flights, which could have data associated with them, like links and therefore fuel costs and stuff like that. And then we can use this to figure shortest path routes, optimize the number of planes to fly per route, all this kind of stuff. These are also used for road networks and logistics, for planning how to ship things from one place to another, electrical circuits, all kinds of things. So getting really good at graph theory and graph data structures will do a lot of good as a computer scientist or a computer engineer or an IT person, because these graphs could also represent nodes in a network, and we're trying to optimize, for example, how many routers we need, how many subnetworks, and that kind of stuff. So graph theory is used a lot, but of course it's based on some of the other types, and it's a more general form of a tree, if you will, as well. So these are all kinds of things that you're going to encounter again. I want you to be exposed to them now, getting into the concepts of representing them and coding them is, maybe a little beyond the level we're at yet, but you're getting close. They'll be a lot easier in the object-oriented world, and we'll do some of these when we get into that. But you need to understand what they are and start thinking, as you think about problems, thinking about what would be the most appropriate tool to use. So again, these will be tools in your tool belt, just like we've talked about before, so you have a variety of tools to apply to different kinds of problems as they're appropriate. Okay, so that concludes the third of the video lectures, and again, feel free to contact me during the week, and I'll see you back in class for live lectures next week. Thanks for listening.